Okay, good afternoon. Welcome to the afternoon session of USP Strategic Workshops. In this first session of the afternoon, we have four guests. We have Professor Anita Marcioli from Unicamp. We have Bruno Vaz from Braskem. And we have Rafael Luque from Córdoba University. And we also have Liliana Manino from Universidade of Venda in South Africa. So we will start with Anita Marcioli, which is a full professor at Unicamp. Is a specialist in synthesis of natural product, chemical ecology, and biocatalysis. And currently, she's leading different projects regarding the application on microbial products and biotechnology, and also have a collaboration with an important company of mining, which is Vale SA. Okay, Professor Anita, please.
Good afternoon. I do apologize for my sunglasses, but I have a really crisis of allergic, and so I'm protecting my eyes. Good afternoon again. Today, thank you, Pedro, for the kind introduction. And I have chosen to show you some projects that are ongoing, and I believe they are really interesting because they try to put together more than one enzyme. And green, to be green, is to make small reactions and to see in a small reaction, small volume, let's say 200 microliters volume, to have all the answers of a reaction. For example, you have to see the enantiomeric excess, the yield, everything. And if you have a nice product and the, let's say, the enantio result of your reaction. And just in summary, very rapidly, we have, we make reactions in 200 microliter scale. Well, in industry, you will say, what can I do to make a scale up to tons in industry? Well, you have to start somewhere, screening, and 200 microliters is friendly. You don't use much reagent, and still you have the answer. You have the correct microorganism and the correct enzyme for your reactions. So we will just have a look at biocatalysis, high throughput screening, then to two enzyme system, transaminase and immunoreductase, and then, back. And lipase peroxide, I will skip that one, and just to show you that these two systems can lead you to a result in cellular. You can have a diagnostic if you have cancer or not. And in biocatalysis, what do we do? Those microscale reactions with a specific substrate and designed to the selective detection of enzymatic activity. These are low cost, effective, and fast. These assays are sensitive because we use probes that are fluorescent, so the signal is very intense, and so you have sensitive assays. You can use any molecule for your assay to detect the signal and to tell you that the enzymatic reaction occurred. We use umbelliferone, but we use also resorphine and lately some synthetic molecules. But most of our work deals with umbelliferone. And we evaluate the catalytic potential of the reactions. I will not go through all these tables, but most of our reactions, they are evaluated following a very simple mechanism. that you have a fluorescent probe, like here, and you have a linker that can be the linker. I will just explain. For example, here, for monoamine oxidases, you have umbelliferone, a 3-carbon linker, and an amine. If you have an enzymatic reaction on the amine with a monoamine oxidase, you will have an imine. This imine will undergo will have water added to the imine and end up as a aldehyde. And this aldehyde, in the presence of bovine BSA, it really eliminates and gives the fluorescent probe signal. You can have TA, transaminase, and also you will have this signal. Well, and just to tell you how this, to show how these occur, you have a 96th well plate, and you can see that some wells are black. They do not have, these are considered negative control. You have a very bright line where you have the positive control, therefore we take 0 negative control and the positive control and your experiment. Therefore you can, with just this survey, you have a survey on 96 reactions. Of course you have to make, let's say, 2 or 3 to have the idea, if you have not, because these are so small that you can have some mistakes. But you make a medium, an average of 3 reactions. With this, you can screen a lot of microorganisms, a lot of enzymes. For example, here you have two fluorescence part. These are resorphine and these with umbelliferone. All of them have the same, you monitor different reactions. And we went further. Not only we went to enzyme, but multi-enzymatic, not only one. We could choose several microorganisms and still simultaneously evaluate 2 or 3 enzymes at a time. Why? Why is that? Because in one well, you can read different wavelength, and different wavelength will tell you which enzyme is active. For example, in this case, we monitored probe 9 with resorphine and probe 11, that's here, that's just esterase. So you could monitor epoxide hydrolase and esterase at the same time. Imagine the amount of reagents that you are really saving. You monitor 96 reactions at the same time. You will say, is that optimum? Are you sure? Well, once we have the result, you have to go back. And for the best result, you do your reaction. Instead of doing 96 reactions, you will do 1 reaction or 2. And just to have an idea how this occurs, so you see here, this resorphine has this is the color. So I don't have to see because my eye is terrible, but I have the equipment who tells me that I have this compound. I have this control positive, and the assay is a mixture of this and this. And it's just to change the wavelength and how you detect. It's a very small equipment. You don't waste reagents and time. Well, to make the E evaluation. You just have to compare the fast enantiomer with the slow enantiomer. Now I'm talking about EE, enantiomeric excess. And for this, I have to have chiral probes. You see, it's different. I have to have a fluorescent probe that will be modified by an enzyme, and then chiral probes that can be selectively modified by enzymes. In conventional experiments, you have both enantiomer competing for the same enzyme, and you monitor by, sorry, this is part in Portuguese, part in English, in HPLC and GC. And here you compete both R and S enantiomer compete for the same enzyme. However, you can do the same experiment here with chromophore, where R and S, they have different chromophores, and then you detect. This experiment was published by Caslausa, and Raymond had evaluated the enzymes efficiency with different chiral probes, R and S, separately. But you have the results are far from reality. You still have to make other experiments to make this work. In our case, we changed to fluorescent signals. And what we did, we had one fluorescent probe for one enantiomer and one fluorescent probe for another. But to have a good result, you have to make a competitor. And the competitor was not fluorescent. For example, you have here a probe that will fluoresce after the enzymatic assay. And you have to put a competitor that does not give a fluorescent signal. So here we just evaluated aspergillus lipase and pseudomonofluorescence lipase, both with enzymes. So you see you have different chiral probes. And we just see how the EE, by just monitoring the signal intensity of the fast enantiomer and the signal intensity of the slow enantiomer, all these in one single plate. And to make a competitor, we didn't want to have it any chiral center. So you monitor the esterase, for example, activity with this probe. It's not a probe because it does not undergo the cascade of reactions, because this to have this fluorescent signal, you have to have a cascade reactions. First, hydrolysis, then you have in the medium periodate, and then you have BSA for the beta elimination. Therefore, this one does not undergo the beta elimination. Good. So we have fast evaluation of, we called it quick EE, and we really monitored several microorganisms and also commercial lipases and esterases, and we could select the best one for the reaction we wanted. We published this in Brazilian journal. The second multi-enzymatic process, because this is what I want to point out. We really try to focus on multi-enzymatic processes. And this one was transaminase and aminoreductase. This project is financed by GSK FAPESP. And the multi-enzymatic process, we had a target. This started some 4 years ago. We were interested in ant components. And in the ant venom, you can have piperidines, pyrrolidines, all these molecules. But we began with the 5-membered rings. And here you have 2 alkyl groups, one at each side of the pyrrolidines. And to monitor which of the enzyme would make this cascade of reactions in good yields, we began with monitoring the diketone with transaminases. The transaminases are commercial, so it's easy. You just have to have all transaminase in your lab. That's not so easy because you need to have the money to buy them. The second thing, you have to have the minute methodology to monitor which one is the best. But as I showed first, we have the 200 microliter reaction methodology. And so we went through, I listed here some of the codexes, transaminases, but we have more. We have a whole bunch of transaminases, and we could see which one was the best. And 1A, 1B, 1C, 1D, 1E is just the same structure, but with different, always with methyl group in one side, and then on the other side we had methyl, propyl, butyl, and so on. So the elongation was made only on the other side. So some of you might ask me, why are you elongating? Because in nature, that's what happens. The ants do have one methyl at one side, or ethyl at most, and elongation at the other side. And as nature evolved in billion years, you do not, you try to follow it first, because it has a way to do things. Here, therefore, when we did all these reactions, we concluded that ATA 117 was R-selective and was one of the best enzymes for this reaction. And then we had, just for you to have an idea, all these diketone were just formulated or obtained by a very simple method. That's chloracetone and methylketone treated with lithium LDA and THF to obtain the diketone. Well, very good. We had that first reaction done. We went to the second one. To have the selection of enzyme for this reduction, for imine reduction, we had to have several compounds with the imino to be reduced. This was obtained by this very simple reaction, and then we treated with several I-red. And of course, we didn't want to use a lot of cofactor, because here the cofactor is an NADP. The recycling of NADP with glucose and phosphate, sodium phosphate buffer. This was done. This was the first part was in our group, and the second part was performed by Bruna Zucoloto Costa, who is my postdoc, I'm sorry, in the group of Nicholas Turner in Manchester. And no, it's okay. It's okay. No, it's okay. No, it's not the code. I'm just like that. And here, finally, we have a one-part transformation going from the system, diketone system, to this. Okay. Finally, to the alkaloids, the ant alkaloids. This is a one-part reaction, an effective reaction, and here we have, but we had collaboration with Nicholas Turner, and he has discovered right recently the ag-red aminase, and this is new. It is not commercial. So this is very good. So these are, if you look at the results, we can go from the ketone to 90%, 99% yield, and to 99% EE. Well, this is very good. When Bruna, who was in England, just told me that, I was very happy with her result and her performance. The multi-enzymatic process, too, is an epoxidation at epoxide hydrolase. But I don't think we have time. I think we only have 20 minutes, right? So I have to rush. And I will skip this process and go to incellulose, because we wanted to see if we could monitor a multi-enzymatic process in a cell. And therefore, well, here I show you, this is Bruno, who is in Manchester and returning now, and Carolina is in Foz do Iguaçu, and Lair is in Campinas. With this, monitoring enzymatic activity in cancer cells, we used resorphine. Why is that? The problem is that cancer cells, or any living cells, they have a blue fluorescence. And if you try to monitor them by confocal, you don't see the reaction very well. But if you have a probe that has a red fluorescence, you will be monitoring the reaction better than if you had a blue signal. We wanted to monitor cancer cells and to monitor phosphatase. Therefore, a phosphate was linked after the linker of 3 carbons. And if we had a phosphatase, there would be a hydrolysis acting then, an alkyl dehydrogenases would make an aldehyde that would undergo beta elimination. So you see, the chemistry is over and over the same. The synthesis, okay, I don't have to go into details, but we could synthesize the probe, and then we had to test the probe. The problem is that you don't see very well, but the OH probe really got into the cells, although you don't see very much. The cell is here, and the control is there. We used non-cancer cell, RYPE, 1 cells as control. And here you have the phosphate probe, right? You have more fluorescent signal. And but this, when you see the image, you don't see how much it is active. We had to go to flow cytometry experiment. And then we were really sure that the cancer cell, that's here, PC3, and this is the control normal cell, you have more activity, ADH activity. Well, therefore, with this probe, we could distinguish cancer cell and normal cells. Nowadays, ongoing research, we have a Mao and IRAD in collaboration with Nicholas Turner. From a Brazilian fungus, isolated from the human skin, we could detect a Mao activity, and now we are buying the plasmid. It should be it should have arrived yet, but it's not. We selected the ATA from 24 ATA from codexes. We could select one that was the best one. An epoxide hydrolases in collaboration with Annette Pereira de Souza and Lilian Bellotti. And a monoxygenase from Bacillus safensis from petroleum has been sequenced and was deposited in Gold genome. Now, the Mao genome, the fungus genome, where we detected Mao and IRAD, we are not depositing. And I will tell you why. Because if we deposit, it's so easy to go there and to select the genome from the genome, the gene that has Mao or IRAD. Therefore, it was kept a while in the lab. From Bacillus safensis is open, okay, because there are so many epoxide hydrolases. And that's what we have. This is Unicamp here. And okay. Thank you. And my group. It's a little bit different now. This was last year, but it's pretty much the same. Thank you.
Now I call Bruno Vaz. Bruno works at the Innovation Management at Braskem. Bruno is an engineer in his formation, but he went to the executive world by doing some formation, and he's going to talk about the importance that innovation and interaction with the academy have in the Braskem business model. Thank you, Bruno.
Thank you very much. First of all, it's a pleasure to be here. Thank you, Vania. It's a pleasure to meet you in person. We visited the university, but we didn't have the opportunity to meet you there. So thank you very much. I need my presentation here. Just a moment, please. So the idea is to make a quick corporate overview and share with you what we're developing regarding green chemistry, innovation, and entrepreneurship within Braskem. We have the United Nations Industrial Development Organization chose Braskem to present his case regarding green chemistry, and we'll talk a little bit about the Lean Startup. Braskem is at the first and second generation, the petrochemical industry, has more than 8,000 members, 70 countries. We have a 230 million investment innovation annually. We have 36 industrial units, and more or less half of our revenues are from exportation. In innovation, we have 300 people, 7 pilot plants, especially in South Brazil, in the Triumph site. We have 2 technological centers, one also in Triumph, another in Pittsburgh. And we have 33 laboratories serving all the technologies that the company is developing, since polyethylene, polypropylene, the basic chemicals, and also the renewables unit at Campinas, developing especially new chemicals and new technological routes. Well, this case that UNIDO selected from Braskem is regarding the use of sugar cane as a renewable raw material. So what's the difference regarding the normal polyethylene and the green polyethylene? We take the ethanol to make ethylene, basically dehydrating the ethanol, and after we have the ethylene, the green ethylene, the polymerization process is the same for the two polymers. So it gave a great visibility for Braskem because not only the process is different, not only because it's a renewable raw material, but you have a completely different interface with clients, with your whole supply chain. It's completely different. The life cycle analysis regarding, for example, the market developed in Asia with this product, it's another client, it's another concept that we have. And it was a learning process for Braskem also. If we take the commercial team from the normal polyethylene, the green polyethylene is a different team. They have a different training because the approach is another. For example, the Japanese market is really concerned about the sustainability, the carbon emission, etc. So it's we have different markets with different approaches also. So Braskem is the world leader in biopolymers. We have a 200 kiloton industrial plant also in South Brazil. This is the UNIDO team that visited us. This is the first global public-private partnership to bridge this gap between science-based innovation and real-world application of green chemistry in developed countries and economies in transition. I would like to highlight the importance of this kind of innovation. Because when we talk about innovation, we can say that innovation is to create value. But which value? So it's important for us to have this link between innovation and green chemistry, because with innovation we can turn resources more available. Since Thomas Edison, since Uber, or since any of these recent innovations that we are hearing about. So, and especially green chemistry respects both sides. You're creating an asset, but not making the liability that we have in another industries, in another process. So it's a great opportunity to create value and also respecting the liabilities, knowing that we have limited resources in our world. And also for Braskem, we always take in mind two approaches. If it's a technology push or market pull innovation. We may introduce to the market, for example, a smart polymer, or the market may request to us a change in the polymer and any characteristics. So it's a two-way street. So we must be connected with the industry, with the academy, with our customers, to know which kind of innovation is important for this moment. It's another picture of this visit at the Triunfo facility. We had several specialists from around the world, from Peru, Germany, and other countries. Regarding Lean Startup, we have this article from Steve Blank saying why the Lean Startup changed everything. And we really believe we can have several applications with this knowledge, with this approach. Because these startups, they build, they measure, they test it, and they learn it. So they do it repeatedly, one way after the other. And the scale-up process is very important also. It's a good learning process for a company like Braskem also. If we are going to make a new industrial plant, how can we scale up? What can we learn with the startups? what they are doing right, what we can learn with them. Internally, we are, for example, one approach is to accelerate a project. We are accelerating an internal project, and the results are doing great because at a corporate level, you have different decisions structures. In a startup, if they decide to make a test, they want to go to market or to publish a new website, a new app, they will just publish. They won't ask permission. So this kind of interaction gave us more freedom internally to develop. For example, we went to the street to ask the potential customers if this technology would be interesting to them. Usually as internal development, R&D, we don't have this, and the Braskem is more B2B than B2C. We are not so close with our customers. Of course, we have the interaction, we have product developed, market developed areas, but it's a B2B business. So what we learned with the Lean Startup, if you have an idea, ask your potential client, what do you think about before spending millions of reais, of dollars? Ask them. Another point also is about risk. Risk is expected for startups. And for a corporate view, risk must be avoided. All the managed process is to reduce risk. But if you are talking about a transformative innovation, it has intrinsic risk. So you're doing the right thing, measuring in the right way with the wrong process. So you need to align it. What kind of innovation you're developing? It's a core, it's a transformational, or it's a radical innovation with the right methodology. So for the right technological platform also, because at Braskem we have, for example, the polypropylene, polyethylene, and the renewable business is another one. So the maturity that we have at these technologies are completely different, and we have to have the right tool. Also, the financial reporting. For startups, they have the metric that matter. For corporate, we have a strong obligation to publish reports, etc. Of course, it's going to maintain, but within a specific project, a small project, could we do anything different? I think we have opportunities here. Especially the agile development. It's a process that at our team, at Innovation Management, we are using it since the planning of our activities during the year, how the metrics of our results is going to be measured, and to develop a new project, to develop a new idea. It has been a great experience to us, especially because if your leader knows what you are doing and what you are not doing, prioritizing the ideas in this process using the agile methodology, you are going to have more speed because you're not going to have a conflict. For example, Bruno, why you are not in the Abikin conference today? Because I'm at USP, and he knows it. So, but when you take more complex activities, it's not so simple to understand which task must be prioritized. So, the agile methodology is helping us to adapt also this a little bit to our culture, but we are obtaining more speed and greater results using the agile methodology. And also, I think the customer also, to hear the customer. If we are going to develop a new platform, we have learned a lot with startups and what we can do together with them. I'm bringing here some perspectives that we may have in this environment. Since events, for example, a green chemistry investment fund, a discussion about it. Braskem has Braskem Labs. It's a mentoring program. We are doing an internal acceleration, especially outside Brazil. It's very common to establish partnerships with startups because we may think, okay, I have an investment in a startup. I have some shares. Is this enough to obtain, to transfer the technology from a small company to a big company? Is this enough? So the partnership model, instead of an investment model, is very common outside Brazil. We have the corporate venture capital, outsource R&D. Are startups a good outsource R&D? Or could we develop a joint effort? Co-working, as Itaú is developing here in Brazil, very famous. Or you can look for this environment to pick the greatest talents. This chemistry, this physician, this engineer is very good. I'm going to hire him. So, I'm going to buy the company specifically due to his capacity, etc. So, we have several visions regarding this market, regarding this ecosystem, and we have a lot to learn. Especially in Brazil, it's a new environment. It doesn't have any. It doesn't have even 10 years. So. It's a great opportunity. Since mentoring for accelerating projects, it has been a worth experience, and I encourage you to make this approach. It's a way that we are finding to bridge this gap between green chemistry, bioengineering, innovation, and the market to get closer to the universities. Venture capital definitely is one way to conduct this process. So this was the main topics that I came here today to share with you. And after, if you have any questions, it will be a pleasure to answer. Thank you.
Right now, we will have the talk of Professor Rafael Luque. She's professor at Cordoba University. And most of his research is dedicated to biomass valorization, including different types and approaches for doing transformation of biomass, including microwaves and heterogeneous catalysis. Luke have impressive publication record with high impact, and we belong to the same green chemistry family also. Okay, Luke.
Thank you very much, Pedro, for the kind introduction, and also thanks to the organizers, especially Vania, for having this event today and for giving me the opportunity, of course, to be part of it. So, my talk today is going to be related to most of the ongoing research efforts that we're currently developing in our group. So, it's going to be a very research-oriented type of presentation. I won't keep it long and very detailed, but you will see that from the expertise of the group, I consider myself, I liked actually the introduction of looking this way. I consider myself as a multidisciplinary scientist, so we actually collaborate with a lot of colleagues in a lot of interdisciplinary research, not only in chemical engineering, which is, as you will see, one of the main topics of our group, but also in material science, a lot on biotechnologies, and even more recently related in the kind of interdivision between chemistry and biology. Some of our interest will be summarized as part of the talk. Okay, so I belong to the University of Cordoba. As Pedro was mentioning, Cordoba is located in the southern part of Spain. If you had the chance to be there, it's a very beautiful city that I highly recommend you to visit. Apart from the science that you will see today, we have a lot of things, additional things to visit. This is our campus, and those were the beginnings of our group. So we started as a very small group now. At that time, back in 2009, see, I was there with my former colleagues, one PhD student, one master student, and one postdoc. This was the group as it was at that time. And the group has been growing in these past 10 years, so we are almost 30 people now. 6 professors. A seventh one is coming with 3 very young assistant professors that have recently joined the group with a national scheme. And the output of the group is not only reflected in terms of number of publications and funding and so on, but a very important contribution towards industrial engagement. Not only by the number of spin-off companies that have been spun out from the group in the past few years, which is also pretty remarkable. We have 3 spin-offs as part of the group in the past 5 to 10 years, but also in the sense of collaboration, a very integrated collaboration with industry, which is something actually very important that I will be happy to discuss later on. And that will take us to some of the examples, of the applied examples of applied research that we are currently involved at the moment. These all obviously stem from a fundamental research interest and based on fundamental understanding of some of the concepts that I will be showing in my talk. So the slide summarizes a little bit the research topics and the different platform technologies that we have been involved in the group in the past few years. We have done a lot of things related to nanoscale chemistry in the design of a lot of different nanomaterials and nanoentities for different applications. Most of the applications have been in heterogeneous photo and biocatalysis, even more recently. And we have now a big platform related to continuous flow processes. This part is very much connected with industry, so you will see some of the industrial examples, not only as part of the spin-off companies or industrial projects that we have as part of the group now. And last but not least, the focus of my talk today will be essentially biomass and waste valorization strategies towards the production of chemicals, fuels and materials and valuable products in general, developing different biorefinery concepts based on feedstock dependent type of approaches that I will show in the coming slides. So this is pretty much a summary of how I have structured the talk. I will keep the introduction to pretty much nothing because we have already seen a lot of introductory slides this morning. And I will essentially focus on the different platform technologies, providing examples on biomass and waste valorization, the design of heterogeneous catalysts for various processes, continuous flow chemical approaches, and then miscellaneous, in which I have included 2 or 3 projects that are currently ongoing. Perhaps, in case you are interested, I can elaborate a little bit more on those, but that reflect actually the multidisciplinary and interdisciplinary character of our group these days. So in terms of green chemistry and sustainability, it's very important for us to focus on a very innovative and novel concept, different from the typical replacing, reducing, and recycle. I like the R's because obviously my name starts with R, but the most important thing is that I bring you today a new concept that moves, in fact, forward towards a more sustainable society. That is the concept of valorization. You're going to see a lot of strategies, a lot of approaches that I'm going to present as part of my talk today that are going to relate to harvesting value actually from waste or from waste-derived feedstocks, including biomass, and producing a wide range of different higher value products, from chemicals to biofuel precursors, fuels, and materials that obviously have a lot higher value as compared to the original feedstock that we are dealing with, and at the same time the valorization also from the philosophical point of view aims to provide solutions towards environmental burdens that are created by some of the features that we have been dealing with, and avoiding the utilization of those feedstocks, of those residues, or completely removing the issues created, not only environmental, but also economic and socioeconomic and so on in our current society. So based on this, of course, we have been very much interested in developing different strategies towards the valorization of biomass and waste-related feedstocks. So this is a complicated slide, but to make a long story very, very short, we have been focusing on understanding, in the first step, pre-treatment and pre-processing strategies towards the construction of the complexity present in biomass into simple platform molecules, simple chemicals that contain multiple functionalities and that we can profit from fundamental understanding of their reactivities, and then translate them back to biomass and to be able to translate their optimized reactivities and to be able eventually to work with biomass and to waste-related feedstocks. So you're going to see that I will show a lot of research related to platform molecules, but you will see that the end of the line and the eventual application relates to the use of biomass and to the use of waste-related feedstocks. So understanding, of course, the chemical composition of this biomass, of these residues, whatever they are, I mean, the examples that I will bring today mostly relate to lignocellulosics, but these are not restricted to lignocellulosics whatsoever. As you can imagine, with 3 spin-off companies and with the large group that we have, we are able to diversify into a lot of topics and to deepen the understanding of this reactivity, not only of lignocellulosics, but a lot of waste-related feedstocks. And I can comment just briefly on a few of them. If you are interested on e-waste, we have been working with companies on the valorization of waste cables, of printed circuit boards, and so on. If you are interested, for example, in nano, we have been also working on nanotoxicity of materials and environmental speciation of nanoparticles in the environment. These are 2 important industrial projects that we have, but we have been also working on valorizing construction materials, for example. We have been also working on valorizing different waste-related feedstocks or local industries from slaughterhouses, for example, from the tannery industry, and these are among the many multiple projects that we have been working with as part of the group. But in all of them, we experience this important take-home message that is shown on the slide. Profiting from fundamental understanding of the chemical composition that is present in the feedstock that you are dealing with is key to succeed in deconstructing, in valorizing this feedstock towards the production of valuable chemicals, fuels, materials, energy, name it. Keeping the whole picture in mind and the big picture in mind, the examples that are going to illustrate this potential relate to the valorization of different waste and biomass-related feedstocks towards a number of separation, fractionation, and valorization strategies, understanding the composition, particularly chemical composition of the fractions that are present within this feedstock. That could be, in the case of hemicellulose, in the case of lignocellulosics, hemicellulose, cellulose, lignin, and other minor constituents. But in the case of e-waste, for example, is the content of metals, is the content of heavy metals that are present, is the content of plastic type of components, PCBs, and so on. And eventual processing based on a number of green synthetic strategies or green processes and green technologies towards the next generation of chemicals, fuels, and materials from this waste feedstock. So I will start firstly with looking at biomass and waste valorization platform technology. And again, I will skip most of the details from the coming slides. So if you are interested, you are welcome to address to me any of these at the post-question section. So we have been extensively working on lignocellulosics from the pretreatment and processing strategies towards differentiation and production of C5 and C6 sugar fractions. And we have been mostly interested in valorizing the C5 and the C6 sugar fractions towards a wide range of valuable products. Furanics are an important part of this type of valorization, including furfural and HMF, and also levulinic acid and levulinates, as you will see, important subproducts and side products of the chemical industries in Europe. I'm going to see in a couple of examples. For the first example that I will bring you, again, is an example that illustrates the potential of these furanic type of materials. We have been working on the production of furfural from C5 sugars. And to make a long story very, very short, anyone can do this, the top part, but not many people have actually done this, the bottom part. So the top part is a very simple dehydration of the C5 sugars to the final product, to furfura. This is pure xylose. You can buy it from Sigma Aldrich. It's relatively inexpensive. It's very easy to work with. And you can achieve good yields of the final product in a relatively simple dehydration step. The important thing, and the take-home message in this particular slide, takes me to the valorization of a biorefinery-derived syrup. And this is a completely different story. When we are dealing with this type of syrups that are indeed enriched in sugars, but in sugars in the form of oligomers, not in the form of monomers, you need to first find a catalytic system or a process or a technology to be able to chop off the oligomers to the respective monomers, and then the monomers undergo dehydration to generate the final valuable product. And this is not such an easy task, because the first thing you need to have the catalyst to be able, or the process, to be able to do the bimodal type of conversion, but also you need to deal with a lot of impurities. And these impurities are going to poison your catalyst, are going to completely kill your catalyst, or are going to create a lot of issues in terms of the process itself. So in this way, we were able to successfully achieve this type of conversion using a particular type of catalyst. It's an ionic liquid, could have been a solid acid catalyst, name it. The particular optimized reaction under these type of conditions was conducted with an ionic liquid, supported on a carbonaceous material or unsupported. But this is, again, just one example that illustrates the possibility to translate the optimized results of reactivity working with pure feedstocks to biorefinery-derived systems that are a lot more difficult to deal with. Talking about furfural, now we have produced furfural out of sugars, and we were interested in further upgrading furfural towards a number of furanic derivatives. Furanic derivatives are very interesting because they have a lot of important applications in the chemical industry. They can be used as solvents, intermediates for fragrances, for other types of polymer-related materials, as we will see later on. And indeed, they can provide additional revenues to companies and a lot of possibilities in the future. So the particular chemistry that was selected for furanic materials was a hydroconversion under continuous flow conditions. And again, to make a long story very, very short, we were able to successfully convert furfural derived from this C5 biorefinery syrup into a wide range of different furanic compounds and even some other interesting chemicals for the polymer industry, pentanols, using and designing different catalytic materials for each one of the steps. So, in case you are interested, copper works nicely for this particular step, nickel and palladium work for this nice step, ruthenium and nickel or ruthenium copper work for this particular step. So we were able to design and to engineer catalytic materials for each one of the steps that are proposed on the slide in order to selectively produce all of these compounds in different types of reactions under continuous flow conditions. Moving on to another furanic material, HMF, that is produced from hexoses. We have been extensively working also with HMF, and in the case of HMF, we chose selective oxidations to DFF, and for this, again, we have been working with another type of catalytic system. It's a heterogeneously catalyzed process using a magnetically separable iron and cobalt MOF templated type of material. Could have been another different type of system, but this one was found to work nicely. We have quite some nice experience with MOF and MOF-related materials. They have very interesting applications, not only in catalysis and in this biomass-related conversion, but importantly in energy storage type of applications, something that I will mention towards the end of my talk at the same time, and potentially even in adsorption type of processes. And last but not least, levulinics, of course, important compounds, levulinic acid, that can be also produced from the C6 sugar fraction from the lignocellulosic materials. Making a long story very, very short, we have been developing different types of catalytic strategies and catalytic nanomaterials that we could eventually investigate towards the different mechanistic insights and providing essentially two different main products: methyl THF from copper-based catalyst, valeric acid from particularly noble metal catalysts and palladium in particular, following kinetics and the flow conditions and the activation pathways, as well as selectivities towards the highlighted products. And why we were working with levulinic acid? Well, at the end of the day, and as I have mentioned, this is a very interesting industrial project that we have now. The reason is that, profiting from fundamental understanding of the known reactivity of levulinic acid, we could work with methyl levulinate, which, funny enough, had an even higher reactivity as compared to levulinic acid. Methyl levulinate is a side product produced in multi-ton scale, close to 30,000 tons per year, of the polymer-related activity of the company Avantium in the Netherlands. So Avantium has the XE process in which they are able to generate PEF, polyethylene furanoate, that is supposedly called to be the new biorenewable plastic of the future that will replace PET. So these guys receive a lot of significant investment from the big giants, including Coca-Cola, including Danone, and so on. And funny enough, from this XE technology, methyl levulinate as well as humins are the two main side products that are generated as part of this process. So we have been making use of methyl levulinate. Actually, both Wei and Laila have been working extensively on valorizing methyl levulinate to a number of interesting products, including gamma valerolactone. We have been using some commercial and homemade catalysts for this particular system that worked nicely. And Laila also is involved in an industrial doctorate with Avantium these days to provide additional solutions to humins. That is the other multi-ton type of residue generated by the activities of the company, of Avantium. And Laila has actually succeeded already in deconstructing humins to a number of furanic type of materials, as well as engineering new materials from humins towards other type of applications, more energy related or energy storage related and absorption type of related. Last but not least, from the lignin fraction that we are able to isolate also from lignocellulosic type of materials, we have been extensively involved in valorizing lignin. Our approach has been mainly directed to depolymerization and continuous flow conditions, more recently, as you will see in the next slide, using a nickel-related catalyst, but also under batch conditions, making use of different lignin fractions that we could isolate, that we could generate using ultrafiltration from organosulf lignin type of processes. We successfully depolymerized lignin, firstly using this microwave-assisted approach, and we were able to generate a pool of maximum 6 to 10 products, simple aromatics that are called to be the new energy carriers of the future related to this. Okay, so a couple of slides on continuous flow type of chemistries. These are more fundamental science, but related to the pharmaceutical industry. We were able to synthesize a lot of interesting compounds that you see in there. From the synthetic organic point of view, interesting because they have biologically related activities. So in some of them, we found some very interesting antifungal, antimicrobial, and even antitumoral activities that we have been subsequently exploring. We have done this under continuous flow conditions, related also to this, some A3 couplings, ion-promoted aerobic oxidations, and more synthetic organic chemistry. Related to the synthesis of triazoles. So triazoles are also important organic compounds that have biological activities, similar to those that I have been mentioning earlier on as part of my talk. Continuous flow photochemistry, moving on towards this type of concept that I have been showing. And for this, in some cases, we have been even working with waste. So the example that I'm showing in there, regardless of the results that you have in the paper, in case you are interested, you can read it in detail. But the take-home message in here is that the catalyst that was designed for this particular example was a chromium containing waste type of material. So we were working together with the tannery industry in this particular example and receiving significant quantities of this chromium waste type of materials. We were able to simply generate a chromium-containing metal oxide containing this scolite phase that, funny enough, was photocatalytically active. So we could use it for the degradation of phenol, which is a common pollutant that is present in wastewater. We can also do selective oxidations, again, in another type of example, using another type of magnetically separable nanomaterial. And we have been working and employing some of the mentioned MOFs in photocatalysis. Also getting some very interesting results. So WEG has been working on this project for the past 2 years. Going to the last few slides of my presentation, in the miscellaneous type of chemistries, I can tell you a lot about nanomaterials and nano entities. In here you have a lot of different reviews from the group based on a lot of different type of materials, including magnetically separable materials, nanoparticles in general, silica-related materials, photocatalysis, mechanochemical nanomaterials, carbonaceous type of materials, nanocrystals prepared using the solvent-related process, and most recently on MOF chemistries that you can read in case you are interested. These are some of the materials that we have been working with, and we are now also involved in the design of mechanochemically synthesized perovskites, again aiming to solar cell applications. So we have a very interesting solar cells, dye-sensitized solar cell that can reach over 20% of efficiency in this particular example that we have just submitted to Energy and Environmental Science. And in addition to this, we have been also working with zeolite type of chemistry in these mechanochemical processes. As part of the industrial doctorate of Laila, together with the company Avantium, she has been also working on these human type of residues, in this particular case to generate the next generation of photoluminescence materials. And she has been creating some very nice carbon dots that are photoluminescent, as you see on the left part of the slide, that also have a very interesting adsorption and excitation patterns that we are currently investigating at the moment. And Laila is very happy to work on this particular topic related to humans. The last couple of slides that I bring also relate on this interface between chemistry and biology that I just mentioned. The first thing relates to the use of MOFs and MOF-derived materials as the new generation of supercapacitors. And from there, we continued and we went on to generate novel bio-nanoconjugates as the next generation of supercapacitors. We have a couple of interesting papers just published. I received actually the DOI while the talks on this morning were ongoing of the Journal Materials Chemistry A. And for this, we have been using proteins. So proteins supported, mechanochemically anchored on porous supports, on magnetically separable systems and carbonaceous related systems. And we found that the presence of the different proteins, we have been using protein from horse hemoglobin, and as well as other similar proteins, we found that this can induce very interesting supercapacitor type of behavior to this type of material, something that we are also ongoing. And the last cool example that I will be able to show also, based on food waste valorization in collaboration with one of the spin-off companies from the group, relates to the valorization of coffee waste grounds that are ubiquitously available in the planet in very, very large quantities towards the next generation of magnetic nanomaterials. So we are mechanochemically inducing a reaction to form magnetically separable oxides based on ion-containing materials, and we have been using them for different applications as CO absorbents, which is something not very fancy, but something that we did with the company very recently and that will be a market product very, very soon, is the next generation of thermal foams for medical devices. So for this, we were able to embed this type of magnetically separable nanoparticles into a resin, put it as part of this very nice prototype that we have in there, that Alina is actually showing. And these magnetically separable nanomaterials are electromagnetically responding. So when you apply an electromagnetic field, they get very warm. They get hot, and the hot is distributed around this. So this is nicely, it can be nicely utilized as the new generation for medical devices to treat some type of bone-related problems in different patients. So for this, of course, for your attention, I'm very grateful. Thanks for the kind invitation and the possibility for me to be here. And I will be happy later on after the final presentation to answer any questions. Thank you.
So, first question, whoever want to ask some first question.
Thank you. All very interesting and very diverse set of work. What my sort of take back here is that still a lot of screening, selection work has to be done. In my lab, we are replacing much of that sort of work by robots, by computer prediction, and to get oversight over all the possibilities is a big challenge. So in a way, we move away from experiments, even smaller volumes than the volumes that you mentioned, and try to really get oversight that helps us faster, larger scale numbers. So it turns from material into information technology in a way. That is the sort of thing that I see happen. With synthetic biology, it's even bigger, I think, than in the chemical sector. What do you anticipate in this case for the topic that we are discussing today, particularly the entrepreneurship thing, because it moves away from labs, it moves away from a lot of stuff that we do at universities. And in my opinion, many of the industries have often much better facilities, more updated facilities than the academic labs. So I see in a way that the academic institutions lag behind in that. First of all, maybe my observation is just wrong. And but if I was right, what do we do with that? Because I always believed that the academic institutions were the church of the wisdom.
I've seen so many theoretical predictions wrong that I don't believe you can substitute prediction, mathematical, or you really have to go for the reaction, the experimental. Let's say, false positive and false negatives are much more frequent in a computer than in real life. That's my opinion. So we are not behind. We are just doing a good thing.
Anyone want to comment?
Obviously, like to comment on that. I think you are partially right on the reflection related to industry and academia. This is something very interesting that I have been also experiencing myself with some of the contacts and the collaboration that we've had with some companies. While I agree with you that in some cases, I wouldn't say in all cases, but in some cases the companies are way ahead now of academia, and universities are a bit lag behind in terms of this infrastructure, I will say. I still believe and I still feel that we are way ahead in terms of knowledge in some cases. So I do not feel ourselves so much lacked in terms of knowledge. I still believe that we are core in the church of wisdom, as you say, but we do have lacking of infrastructure, facilities, and I guess this is in the past few years reflecting back on the bad funding situation for some institutions and some countries. That's for sure.
Yeah, my observation is this. I'm a lot around in industry labs, and I've reviewed many programs around the planet. So, of course, I try to exaggerate in order to get an opinion from your side that may be clear. But I see that within the industry environment there is a lot of good knowledge that is there, and that in many of the cases that insight is really there. I think we make a big mistake if we at academia neglect all that capacity. On the other hand, much of that knowledge doesn't always find its way. In many of the cases, there is a pragmatic solution sought and not a fundamental thinking. So there's much information that actually isn't used, which is a pity also for the company perspective. So my feeling is that one way or another, at the moment, intellectual property side of it is done well. That also companies would benefit a lot from contributing that, and that is what you actually see in some of the fields happen. Companies like Tesla put all their IP on the web and to give everybody access. The open access side of it is increasing. So with that trend, you can disagree with me. That's of course that's perfect. Happy to hear that. But with that trend, shouldn't we bring in more of that information then also in our programs? Make sure there's more interaction. Make sure there's all this sort of things, because maybe sometimes governments put in more money, but usually they don't put more money into academia.
May I just point another little thing? Academia always start from scratch. You build the knowledge. You get students that are just from undergraduate or just masters. You get the doctors, so you can go further on. You choose the right people and keep the right people to work for you. We have to renew our people every year. Every year we get people that are untrained, that we have to teach them from scratch. So that's why academia never goes further than a certain level. And industry can go beyond. I'm absolutely sure that you can go beyond the academia, because we are always restarting from zero. And the students are always zero, and you leave at a certain point, and then the industry just take them on. Okay? So you can go further. We cannot.
I would like to add that, but that sometimes the industry doesn't have this allowance to make this scratch. That screening or beginning from scratch. That's start from scratch. So that's another point to highlight how important the universities are, not only for but this integration is important. Since the highest level that the university may achieve, but the scratch is also important for the industry. For all levels, undergraduate, graduated, masters, PhDs, they all can be integrated into the industry.
Yeah, if I may. Something that we did discuss this morning, Luke, and that I would like to again emphasize is the importance of this interaction between academia and industry. Both parts can be greatly benefited because of this interaction. And this I have been showing as part of our research, but not only as part of our research. This is something that you see in the real world these days, because we academics need industry, and the industry actually needs us in order to continue progress. They need our knowledge. And I'm not saying that this is an easy process. I mean, this is perhaps the most difficult thing that academics perhaps find these days. Because for industry, it's relatively easy. They have always consultancy, they have always other types of activities that would obviously complement their expertise. But for academics, in fact, going from fundamental science, going to fundamental to the basics, all the way to applied research, and all the way to something that you can really put into the market, it's something very important that completely broadens your horizons and completely broadens your mind. You get to experience different important approaches, and in this way, I think this is absolutely the way forward.
Yeah, and in my opinion, it is not the knowledge in itself, it is the people that we bring, because we talk about the same set of people, the ones that start in our curriculum and that go to essentially to the industries. But the reason that I bring up the point is not to sort of have two parties that are opposed to one another. There should be a good collaboration, I think, but it is even beyond that stage. Entrepreneurship doesn't the topic is entrepreneurship of this workshop. The entrepreneurship within most of the industry starts with starters. You know, there can be an ambition, there are business targets, but in my time in Shell, for instance, I think 90% of new process inventions came not from the company. They came outside of the company and being brought in. So to me, the benefit is very clearly there at the interface, and that we are looking for some kind of convergence in that thinking. So with all the information that is around in industries, I find that the dialogue is sometimes very in Dutch you would say flat. You know, we come, they pay us. That's the sort of thing. And my interaction with industry, apart from indeed sometimes there's a lot of help from their side, but it is mostly through my alumni that are now in quite a number of industries. The discussion starts, you know, there's confidence built, there's a certain level of trust, and the real interesting problems also pop up. The problems that I would like to focus my science on. So this that mutual interaction that is even more important, I think.
So I have also a comment on that. For instance, what do you think about, for instance, using, for instance, research institutes as, for instance, as partners for reducing the risk from certain process that industry is interested in seeing? Do you believe that could be the future, or you think there is another model for that?
Well, I guess that this is something that we could discuss. There's not a simple answer to this question. From our experience, this can act as an important intermediate between academia and industry, and certainly will facilitate things for academics. As I just mentioned, this is a big problem for academics. I see it myself on a daily basis, because moving from fundamental and basic research to very applied research is a significant challenge, and not everybody is able to take up this challenge. So the easiest thing is obviously to stay in fundamental research. This is what I can keep doing for the rest of my life. I publish papers. When I'm not publishing paper, I'm teaching, and so on. So, but this important step actually could be taken forward by an intermediate connection, from which, from my point of view, research institutes could play an interesting role. But it's a very difficult transition and a difficult communication between the three parties. So,
I think that the first thing is that industry never gives you a very small question to work on. They give you something, but they don't give you the right, the goal. They just give something for you to mess around. The dialogue has always something in between. That's the industry. And the academia, they don't have the same language. They don't come to you with a straightforward question. That is the beginning. The beginning should be a straightforward question. Then it would be okay. Most industry have it's fuzzy.
The most successful projects developed by Braskem together with universities, they had a strong relationship process behind. It's not a line of credit. Take $10 million, your assets, you have your liabilities, it's cash for the company, you go to the university with a cash and start using it in the lab. So it's a dialogue, it's a process. So it takes time to develop a successful technology. So that we work together at Braskem with the finance team, for example, for funding resources, and we align with them. But for which university are we looking at? Do our researchers, do they know the other researchers? Do they have common projects? Did one PhD from Braskem, did he go to Germany to study, and then he had some friends, some colleagues, and after that he starts working with them, and suddenly this professor might be in São Paulo. Then you have a relationship, but it's not so quickly. Not unfortunately as we would like to have this. It's faster maybe, but it's an important point. It's a process. It's a relationship, step by step.
Any further question?
Well, in this discussion, it's very much concentrated in academia and the private sector. I would like to ask your opinion about the other part, which is normally the government, and where I think it's already mentioned here in the morning, some difficulty because of the political process. It's always very short, and I'm sure especially in this theme from green chemistry, and for example, it was told about waste, trying to give value to waste, and there is a lot of waste in a city, and how could we try to bridge this difficulty that maybe if we are discussing with one particular government, then after 4 years it's another, and the continuity is somehow difficult. If you have any opinion about that.
During the morning, our German colleague shared with us an excellent perspective. Companies look for funding for the wind blades technologies, and I think it's good if we have an open market, if we have liberty, if we have the freedom to act. It's already enough if the government allows it. So I think this Brazilian cost, as we say, sometimes the government makes some efforts to reduce it, to make the industry more attractive for investors. But I think the free market, our open market, would be better for the industry. A real competition. A real competition where you're really good at what you do, when you have the best people, when you have the best technology, you don't have to have another incentives to sell more. You don't have incentives to attract people. They want to be there because the best place, the best company, where they want is exactly where they want to be.
I'm not really talking about giving incentives to enterprise. I'm talking about talking directly with the city that manages, for example, the waste of domestic waste. So you see, it's like we have domestic waste. There's a lot of value there, and someone could take this and try to make like biogas or something else. But then you are talking on not really directly with sometimes directly with a company if it's done by a company, but normally you are talking with a government. So, but the government is changing all the time. That's what that was the point, the main point. Not really, not on the federal level or on the state level that are giving incentives for enterprises, and as mentioned. I mean, talking directly with local problems, as more or less on what she was in a much more micro level. I mean, a little bit more on the city or the state, because of this political process. We are always talking with different people. We're just discussing this a little bit because in a company normally you hire and you keep this guy for a long time so he can develop all this idea for a long time. In the academia we have the time of the formation of our students, but in the political level we have the time of the election, which is normally 4 years. That's more or less what I was pointing out.
Something that is sustainable. You don't depend on the government. Anything that has to work it has to be independent of any government. You don't have to rely on governments. That's terrible. And in our labs, I was successful when I was independent of any financial support, just with what we had in the lab. Then it was successful.
Oh, very nice. I like when yeah, you can, I think, explain why you are thinking like that, because actually I think it's a matter of integrate activities. The university has a role. If you are talking about the Humboldtian idea of the other brother, I mean, not the Alexander, but what it's important to try to do what we should do to educate people, to discuss this kind of controversy, how can I say, it's not only our problem, but we need to educate people to face, to deal with this, to try to find solutions, and also, of course, using good chemistry, knowing very well and also to dialogue with different people from different areas. So how to do this? And I liked a lot because you talked, I think all the talks were, again, very connected, and you use a very strong word, I think, for green chemistry, valorization. I mean, the new generation of green chemistry, valorization. But it's not only about money. And you too, Liliana, and of course, Anita and Bruno too. But you mentioned that we should see the profit. But I don't think, when we have to look more than we are usually seeing. So what is profitable? So I think it's so connected to green chemistry. And we can find local solutions. And we can also have a kind of parallel way to do this without depending so much of this big context that sometimes we are shocked. I can't say this. Sometimes we are so shocked to see what is going on. Yeah, but this is also science. We are made, I think, with the same matter. We need to see this, and we need to discuss, and also, of course, do research, outreach, and everything that we should do in the university, but also with very good companies. So I think it's a matter of integration and dialogue, to speak different languages and to be open to really do what you have done now, to talk. Yeah? So, yeah, so please open your mouth. You can do it. It's important.
Any other comment or question? Okay, so we are at time to close our session. Thank you very much for all of your valuable comments and presentations once again.
So first, I'd like to invite Glaucia Mendes Souza to come here. It's a very long, short CV. Nice to meet you. So, Professor Dr. Glaucia Souza holds a degree from the Biosciences Institute of University of São Paulo in biochemistry, at the Institute of Chemistry, postdoctorate in molecular genetics at La Jolla Cancer Research Foundation, and another postdoctorate in molecular genetics at Baylor College of Medicine. And she's an associate professor here at the Institute of Chemistry and leader of the Sino-Transduction Laboratory at São Paulo University. And Dr. Souza also coordinates a very important program, the FAPESP Bioenergy Research Program, we call BioN. And now I'd like to give you the word, because if I read everything that we have done, yeah. So thank you very much.
Thank you. Well, it's a great pleasure to be here. As Vania mentioned, I am a professor at the University of São Paulo at the Chemistry Institute. Now I am a full professor, not an associate professor, so sorry you have the old version of my CV. And I also have a second hat at FAPESP, where I lead the FAPESP Bioenergy Research Program. For those of you who are not familiar, FAPESP is the State of São Paulo research funding agency that funds research in all areas of expertise, of research, but only in the state of São Paulo, so it's a state-funded, it's about state-funded research that I'm talking about. So I chose to speak a little bit of what we have done over the last 3 years at FAPESP, which is a global assessment of bioenergy sustainability. This was done under the aegis of SCOPE. SCOPE is, it was created in 1969 to aid the United Nations Council on problems of the environment. And since then it has produced many different reports understanding how humans affect the environment, or also studying issues where the environment will affect humanity. And for this report, they chose bioenergy because they thought it was an important issue that was an emerging issue for global problems. And then they chose Brazil as an important player in this area, and FAPESP to organize this report. So I led this work in collaboration. So it was a BioEn, Biota, and climate change programs of FAPESP. FAPESP has 4 main programs: bioenergy, climate change, and biodiversity, and also e-sciences. So those are programs that are more integrative. They are programs that are seeking solutions for problems. So it is applied research. But as I mentioned, FAPESP funds all areas of knowledge. So during this work, we decided to do an analysis of what was bioenergy status in the world, what was the potential for bioenergy expansion in the world, and why we wanted to expand bioenergy. So this was done with 137 experts from 24 countries, so it represents quite a lot of opinions and different views of bioenergy in different contexts. And then there was a scientific advisory committee. We chose to explore how bioenergy interacted in the energy security, food security, environmental and climate security, sustainable development and innovation, and what were the gaps of knowledge. So green chemistry comes up a lot. There's a lot of new technologies coming up that integrates biofuels production, and then bioenergy will come up in many different forms. It's liquid biofuels, it's co-generation bioelectricity, it's heat. So there is a lot of biogas, so there's a lot of different aspects that had to be evaluated. And we raised all the numbers, the examples, the issues, the solutions, and you can find, is this where I point? Yes. Not here. Okay. Okay. So Luke was a participant of this process, and he can tip in if he finds that I missed some important points later on. You can download the whole report. It's an e-book, and you can also contact us if you have any doubts. We paid a lot of attention to the policy issues. SCOPE is an institution that aims to use science to inform policy. So we as scientists, the group was composed of scientists, but the scientists that came from all different areas of expertise, and then we try to summarize the work in very different ways so that we could get some messages out. And I think one important aspect is that we have to have integration of policy so that bioenergy can expand in a sustainable way. So this is so that we can find the right synergies that we can increase the benefits of bioenergy. But I will focus my talk, so there's a lot of different aspects that we have to evaluate, but some of them came recurrently throughout this process. And one is meeting demand, biomass demand. So we're talking about if you're talking about biofuels or bioelectricity or biogas or biochemicals that come from cellulose, hemicellulose, come out of plants and algae, you have to meet demand. So where are we going to put biomass production in the world? What kind of plants are we going to grow? What are the best options? What are the new technologies? Where is the innovation leading the way? Then we also have a problem because we are competing with oil, and that's where the money is, and we have to lower costs, basically. So how can we address the high costs and technology complexities of this new way of producing energy and chemicals? Then there was a lot of talk on governance and financing this new effort, and we now have, since then, a lot of new initiatives that Brazil participates in. So BioAir now is participating in the BioFutures platform and the Mission Innovation platforms, which all gather different countries to answer the COP demand, the climate change demand. So what can actually be done to address trade? How is trade going to evolve, and all the certification and social aspects? Because when you're talking about sustainability, you have all these different aspects, including social, and it was something that we need more studies on social aspects. So the work evolved in a way that we gather background. So you will find 13 background chapters. Then we put all the scientists in a room for 1 week in Paris at UNESCO and discuss the crosscuts. So those are the environmental, climate, energy security, food security, innovation aspects. Then we had to summarize this in a technical summary, which was very tough to come with. It's very easy to write 700 pages, but it's difficult to make a scientist write 20 pages or something of this enormous complexity. So it took a lot of time. Then an executive summary, and then later on a policy brief. And this is a 6-pager, so it's even more difficult. And then a press release, and those were several because we launched this report in many different places. So what are the main messages if you really want to change the way the industry is perceiving bioenergy, the way the governments are perceiving, how scientists are working towards improving bioenergy? So you can also download the policy brief from the bioenfapesp.org website. These are all the countries that we covered in the report, so it was very comprehensive. And we came, we started the study when we did not have, so we are at a point where bioenergy is expanding, and there is a lot of interest in the aviation sector to use this new option. But if you look in the world energy matrix, there is not a lot of modern bioenergy being used. It's only 3.5% of the world's energy that's coming out of modern bioenergy, which is what I was talking about. And then out of this modern use, which is here on the right, you have only 2.6 exajoules that is actually liquid biofuels. So it's really not a lot that we have been able to produce. So can we ramp this up until 100 exajoules? And when we mentioned in the first meeting in Paris that can we do 10% of the world's energy out of bioenergy? People were mad. No, don't talk like that. It's so much, like so much. People will be scared that you're going to be using so much energy in the future out of biomass. But nowadays, that's the scenario. Okay, IRENA has just released last year in 2016. IRENA is the International Renewable Energy Agency. The plan is to actually go even further than that. So it's urgent. We have to do it. We have to find ways to do it more efficiently and quickly. We have to deploy in an accelerated manner. Most of the rush is because of the transportation sector, because, okay, we have electric. That will be great if you have a renewable source for your electricity, but we expect to have only 20% of the cars running on electricity or hydrogen by 2050. So this means we are still going to be using 50% of gasoline in the cars, and the rest has to come from biomass, from bioenergy. So how can we meet these targets? The good news is that there is a lot of new technologies coming up. So what we found throughout the study is that we have in many countries so many initiatives that are taking off. In some countries, biomass came to represent a very significant amount of the electricity, of their energy. So we are able to displace the fossil industry, but there is a lot, of course, to work on. So the report has a number of cases described. There is one chapter that's really interesting. Those are case studies. But you will also find technologies that are well established, ready to go. There's no big deal. We can do it. Okay? Now, in the aviation sector, every time I have to present, I have to go look it up, because there is a lot of new developments. You may not know, but you probably already flew renewable. So there is a lot of blend certification efforts, a lot of fuels that are out of many crops. So we have already blends in jet fuel with cooking oil, jatropha camelina, sugarcane, farnesene, up to 10% blends. There's no problem with the engines. Everything is okay. So this sector is moving on. But in average, what the contribution is expected, and these are many different studies that we summarize, is that we're going to have at least 25% of the global matrix using biomass. So I'm not talking about 10% anymore. We are talking about this 25%. Is this really going to happen, and how? One of the issues is that we see a lot of governments or politicians or policymakers thinking there is not enough land in the world. So this is basically wrong. It's a wrong idea. It's a wrong view of the world. If we want to ramp up to 10% of the energy matrix in the world with biomass, that would be 100 to 200 exajoules a year. We would only need 50 to 200 million hectares. And we are using nowadays less than 13 for all the biofuels that we are making. That was able to displace the economies, the oil economies, in part in many different countries. Out of this, less than 13 million hectares, what we have is mostly sugarcane ethanol, maize ethanol, soy, oil palm, rape, biodiesel, renewable diesel, HVO, and biopower from pellets, from wood pellets, different wood materials. All of them, what our conclusion is that all of them reduce greenhouse gas emissions, all of them, to different degrees. Sugarcane being the most efficient with 76%, but maize also reduces in 42%, and the best is to substitute for coal. When you substitute coal with biopower, you can reduce 93%, up to 93% of emissions. All this land that is used to produce these biofuels is actually corresponding to a Nicaragua. These are the 13 million hectares that I'm talking about. Okay, if you want to substitute for this 25% of the bioenergy in the world, we would need something like a Spain. And if you want to have an idea, because it's kind of difficult to imagine hectares, as some people don't know exactly, I didn't, but all the urban areas in the world correspond to 100 million hectares, okay, if you add this all up. Crops, all the food, 1.5 billion hectares. The total land is 13 billion hectares that we have in the world. If you consider the bad bioenergy, which is burning wood, and it's difficult to know how much land we are using, then you can go up to Ireland, UK, and Iceland altogether. Okay, so that would be all the bioenergy in the world. So what is else? We have all the forests, 3 billion hectares. Then we have all the others, which would be the deserts, the waterlands, the areas that you can't put any biomass. And then look here, all the pastures. If you add Canada, USA, Mexico, Peru, Brazil, and Argentina, all this beige area here, this is all the pasture that we have in the world. So the idea is actually we don't need the land that's used for food security. We have a lot of pasture that is used inefficiently. We need to intensify, improve pasture lands in the world, Brazil included. And remember that we have 40% of pastures that have no livestock on it. So it's just land that could be used for other purposes. We have to address the fact that some of this land is not good enough for food crops, but they might be good enough for energy crops because they don't need so much fertilization, etc. But we need to improve crops to use in these areas. So those crops will need to become high yield, fast grow. They have to produce year-round because oil refinery never stops, and they want the same for a biorefinery, can never stop. And you have to have crops that are tolerant to drought. Remember, climate is changing. We have climate change that will affect agricultural production, so we have to see how this goes. And since we are in Brazil, I have to talk a little more about sugarcane, but the study conducted covered all the different feedstocks. But this is the industry. We produce biomass, sugar, ethanol, and bioelectricity, and vinasse that goes back to the field, so we recycle nutrients. And this is where we want to expand. So the BioN program is aiming at developing the sugar chemistry, the alcohol chemistry, oil chemistry to produce different chemicals, different bioproducts, different biomaterials. So bioenergy could be a driver for the bioeconomy in the larger sense. So we also work in different aspects of the bioeconomy. What we would like to have is sugarcane in some point becoming something like this, where you can have, this is a refinery in Norway that is already using wood to produce a number of chemicals. So we don't have this in sugarcane yet. We would like to have this up and running soon. The other aspect is improving yield. So the yield, current yield of sugarcane is 80 tons per hectare. The potential we calculated is 380. So there is a long way to improve. There is a lot of talk recently about the energy cane. I'm talking about sugarcane, but the new cane is coming, which is, there are two kinds. One that is more fiber rich. Those could be more useful for biopower, for bioelectricity. And the other one still has sugar that you could integrate into first generation, second generation, do both sucrose, ethanol, and lignocellulose ethanol. And the yields are expected to double by 2030 using the energy cane. What I do in my lab is to do the genomics, breeding, biotechnology side of things. At the Institute of Chemistry, we are working towards developing a genomics platform that can help breeders. So we integrate transcriptome, the genome, we sequence the genome with metabolomics. So we are trying to develop gene networks that can help us identify gene targets for breeding or for biotechnology. And this is a network for cell wall production in the energy cane. So we know the master switch, we know the secondary switch, we know the links to drought response. So this all tied up together, and we are looking at how we can change these genes or use this in a platform to help the breeders. We also created Bioen together with USP, Unicamp, and Unesp, the three state universities, have created the State of São Paulo Bioenergy Research Center that is funded also by the State of São Paulo government. And as part of this, we created the Systems and Synthetic Biology Center, which is going to be here in this campus, very close to here. I don't know exactly, but the building is already up. And we are now, we hired new faculties. So we have, I cut that slide, but we hired new faculties for all these institutes. 20 new faculties are starting to their careers. Pedro Vidinha here is one of the recently hired researchers in this center. And we are very interested in collaborating with anyone who would like to. And I want to end by inviting you to our conference, Be Best, October 16 to 19, Campos do Jordão, in São Paulo. Be Best is the Brazilian Bioenergy Science and Technology Conference. It's an international conference, and the abstract submission is until August 6th. So if you're interested, send in your abstracts, or if you are interested in participating in any other way. Myself and Luke, Luke, are the chairs of the conference. And thank you very much for your attention.
Thank you very much for your very interesting talk, and also very interesting event. I think we will be there, and our students too. And now I'd like to invite two colleagues from Granville, and actually Wesley Ambrosio will present the technical part, but also we have the other part to also be here for the discussion. And just to read, Wesley is a chemical engineering and at Unicamp, and he has also MBA for at the Fundação Getúlio Vargas, or Getúlio Vargas Foundation, and he has more than 25 years working in the oil and gas sectors and the agribusiness and the biofuels and a lot of renewable matters. So thank you very much to be here and to attend the meeting. Thanks.
Thanks a lot for inviting me. Good afternoon, everybody. I believe Glaucia's presentation gave me very interesting points to link, because what I'll show you is just a presentation about GrandBio. GrandBio is a company that is actually putting in industrial scale some of the elements you have described earlier in terms of the science applied, but at real scale. So what we're trying to do is to really build the bridge between science and the commercial application and the market. So I will show you some slides regarding the company, and the idea is not to make a commercial for GrandBio, but I would like to show you the kind of challenges we are facing when we bring from the microliters to the several cubic meters, the 1,000 cubic meters reactors that we have and that we're dealing with in our business. Okay, this is just the structure of our company. So GrandBio is belongs to Gran Investimentos, which is a Brazilian-owned family company. And we have another business, which is Gran Energia, which is more related to oil and gas. Our structure, when we created the company, we understood that we would need to do some research. So BioCelery is our research company that makes research in biotechnology. BioVertis is our also research company which works on developing energy cane, initially looking only at energy cane for second generation biofuels, but today we also see this the energy cane as an opportunity for the first generation ethanol business as well. So we're developing, today we're commercializing our energy cane also for the first generation. And finally, BioEdge is the company that holds our industrial assets related to second generation ethanol production. In terms of biomass solution, the feedstock that we use today is sugarcane straw. So the straw remaining from the mechanical harvesting of sugarcane is used in GrandBio to produce cellulosic ethanol. We have the capacity, and we have already done around 400,000 tons of sugarcane straw collection, baling, and storage. So I believe this is one of the largest operations in the world for this kind of biomass collection for a single company. Doesn't look like exactly technology, the type of technology we're discussing here, but this is the kind of challenge we face when we want to take a waste, right, and make it become a feedstock, right? So all these operations were developed with the support of the industry, and this is part of our know-how today, which is, let's say, biomass is probably the second most expensive element in the production of cellulosic ethanol. So handling this properly is key to be competitive in the market. This is a storage area. This storage area no longer exists. So this is one of the biggest learnings we had. We had 3 fires in this storage area. So we learned that this is not the way to do it. So part of the learnings, part of the things that we don't look at when we are developing a technology, but this is the type of challenge the industry will have to deal with. What we have changed basically is we don't store this amount in the same place, so we basically spread this in different storage areas in order to really mitigate the risk. And this is one of the challenges that the industry is facing, not only us, but if you look at the news, DuPont had the same kind of problem in the past with their storage. So we are learning a lot together. Energy cane. This picture here is it's not from a commercial production area. This is our breeding station in Alagoas, and this is the original idea. It was energy cane to make cellulosic ethanol, so very low sugar, very high fiber. But what we're looking today is to find something in between this kind of plant and the sugarcane that we have nowadays in the first generation. But this one is a commercial plantation, so it's easy to see here that both sugarcane and energy cane were planted at the same time, the same conditions, in the same place, and it's safe to say that you can make twice as much biomass per hectare with energy cane compared to sugarcane in any condition. So it's really why I think it's a great opportunity for the first generation as well, because in terms of sugar per hectare, we make more sugar per hectare here in energy cane than in sugarcane. So this is the developments we think will come when we start applying energy cane in the first generation ethanol industry. This picture is just about our breeding station and where we have our experiments. So it's not only in the Northeast, it's all around the place, in order to really understand what are the varieties that will work better in the different regions. This is just a picture that we like to show to see what is the potential. If you look carefully, there are some people here, right? We are in the middle of Bahia, in a very dry area, and there's a big potential to create value in this kind of land using this kind of plant. So there is a big value to be unlocked here. Talking a little bit about our industrial operation, this is Bioflex, which is our cellulosic ethanol plant. Okay, if you look at this plant, is co-located in a traditional sugarcane ethanol. You see the sugarcane plant behind, and this is the Bioflex plant. So it's not a pilot plant. This is an industrial facility that I will show you some data, but here we try really to apply all the science we have been described, but this is not enough. The problems we face are not related to the efficiency of the enzymes, are not related to the efficiency of the yeast that we use to ferment the C5 and the C6 sugars. We reach the expected efficiencies, but overall, this is not the most challenging problems that we face today. There is when the academy works on developing enzymes and yeast and modifying the microorganisms, it's very important because it doesn't work without this, but we have to have the engineering working to make all the rest to work. And so I believe we have the technology risk behind us today, because of course we need to improve the efficiency of the enzymes, we need to improve the yield in the fermentation, but what we really need to overcome is the scale factor. This is the most important leverage for reducing the cost of ethanol. This plant was designed to produce 80 million liters per year, and actually it produces something like 40% of that. No plant can be profitable operating at 40% of its capacity. It was, let's say, a risk taken by the pioneers. We know today how to fix that, now how to debottleneck the plant, so we understand now where the problems are. The good news is that the technology risk that we were worried about in terms of will it work, will the C5 and C6 become ethanol really, it's behind us. So what we need today is to develop the equipment and the reliable type of equipment to make this kind of plant work and create scale so that this business can really be profitable. And this is not rocket science. We're talking about really engineering challenge. So academy and industry working together will make this new industry become a reality. What I would like to emphasize is that this is not technology for the future. This plant exists, this plant runs, we have produced ethanol, we have been certified in California, we have exported ethanol and generated the rings in the United States. So this is not a theoretical business model, this is a business. And what we need now is to increase the scale, to reduce costs, and make the second plant, the third plant. And I believe Brazil is the country that has to lead this new industry. It has all the elements necessary. We have sun, we have water, and we have the area to do so, and we have the technology, which is very important. Some pictures regarding the plant and some data. I have already said this was the nameplate capacity. Today we are not operating at this level, but we know how to get there. This is our first cargo of ethanol that we have exported this year to US. This was the investment in the plant. We know today that we don't need that much money anymore because the technology has evolved in a way that the second plant would require less capex. But again, this is the cost of the pioneering. And we have also an investment on the boiler to generate the power and the steam for that plant, which was additional $75 million, which is not necessary in every case. I mean, if we would build a new plant like this in a different mill that has the infrastructure, the boiler and the power facilities, that part of the investment could be much less. So it could be a different story. R&D, GreenBio in the beginning has this vertical model where we had a research center and we have developed our own yeast and our own enzymes. It was necessary at the time. And today, we believe the best way for GreenBio is to collaborate with other research institutions, bringing our knowledge and putting it together so that we reduce risk and reduce cost. So this is we are reshaping our research strategy, but we still have this is as one of our strengths. That's it. Thank you very much for the opportunity.
Thank you very much. So it's impressive, really. I'm very happy to know what you are doing now. And you are right, it's the present. It's not the future. And yeah, I agree. I completely agree. So thanks. And now I'm very happy to introduce Professor Carlos Greff. It's a very nice colleague, but also friend. A lot of people here, I think, are friends too. But Carlos here has also an impressive CV, and I asked a short one, and I just discovered that you are now the pro-rector for research at the São Paulo State University. He's also a full professor there at the physics department in material science since 2006, and is also the former coordinator of the material science division in CAPES. And we have also here Carlos Sampaio, who will talk about another area. And until 2014, from 2009 to 2014, the scientific director of the SBPM of MAT. Yeah, it's missing here. From CNPq here in Brazil. And the main research interests are on nanomaterials, organic semiconductors, electronic magnetic resonance and electronic devices, and bioelectronics. Thank you very much.
So I'm very pleased to be here in our sister university, USP, and very happy to receive this invitation from Vana and also from Hamilton. And I'll talk a little bit about our research in the field of solar cells, and I would like to just very briefly talk why we are interested in solar energy. As you know very well, we are running on this problem of having so many fossil fuels that is changing our world, and of course that the main source of energy here is the sun. We're talking about biomass. Biomass is converting sun into chemical energy, and the fuels that we are using nowadays, petroleum, is this biomass that stayed for millions of years. So we are always looking for the energy from the sun. And if we could convert this energy of the sun directly into electricity, this is photovoltaics, we would learn that we wouldn't need so much area, as was pointed out by our colleague, the biomass, and we could maybe solve this very easily. But I think maybe I missed the talk of Carleo. Maybe have already pointed out this before. The interesting thing that I would like to point out is that Brazil, of course, as already mentioned, is a perfect place to use this sun energy, either in biomass or for photovoltaics. And here is more or less the map of the sun distribution. And as you can see, especially in this big area where normally it's not so much useful for agriculture and for people living there, we could produce this new generation of sugarcane, as was already mentioned, but also use it for photovoltaics. So photovoltaic cells, as Carleo must have already told, is already commercial, and the basic technology used is based on silicon, the same material that is used in our electronics, but it's a simpler material than the ones in the chips. And there are some problems with this technology. First, from the green or the environmental point of view, it's basically converting sand into this very pure silicon, and this has many environmental problems. And of course, the current technology uses what is called a monocrystalline material, which more or less makes it difficult to make large areas. So you can make it in small areas, so you have to make a lot of connection in the current technology. So there is a lot of things that could be done to improve this technology, not using silicon. That's the point that I would like to point out, as already mentioned. So here are the current technologies and the efficiencies of all the solar cells in the world. And I would like to point out that basically what I will be interested are not on the high efficiency, which are very complex and very expensive materials, but for what we call the third generation, which are these new types of cells that have potential to compete with silicon, basically on the basis of being low cost, as you already seen in the morning for organic photovoltaics. Okay, so basically, as you have seen, as you can see here, these cells are ranging from efficiencies up to 20%, and the commercial silicon solar cells are 12%. Okay, so I think we are quite close to doing that, but of course that changing a technology that's already in the market is not as easy as that. So I'd like to very briefly, just to give you an idea how the PV works. So how can we convert sun into electricity? And the idea is quite simple. It's basically when you shine light, you make what is called an electronic transition, and then you create these excited states, basically charges. One is positive and another one is negative. And what you have to do is to collect these charges, and that's how it turns into electricity. So the basic idea is very simple. You shine light, you generate this excited state, and then you separate the charges. And the important thing is that you have to collect these two charges. Otherwise, it doesn't work as a solar cell. If it collects just one charge, it's a photoconductor. So you have to collect the two. And so there are many challenges from the point of view of material science, especially. And what I would like to point out are just a few of these problems that we are dealing in our laboratory. One of them is on the counter electrodes for dye solar cells. The dye solar cells are basically quite simple in principle. It's very simple to make. Everything is done on low cost. And the idea is basically that you have a molecule that is a high absorber. Okay? It absorbs the light, creates this excited state, and then you have this charge transfer that you need. You need to collect the two charges. So the electrons are injected into a kind of mesoporous structure, and the other part goes into a liquid. So that's why it's a little bit different from the organic solar cell that was described before. And it has a lot of advantage, like very low production costs. We do this always technologies like screen printing, the same that is used for printing T-shirts. It's everything very, very cheap. And we can go up to 13% of efficiency. So this is more or less the electronic scheme, and basically what we are being discussing is just this part. So as you can see, all solar cells have many parts. So typically the electrodes that will collect the charges, the semiconductor that will absorb the light, and that's basically we are concentrating just on this counter electrode, because typically the counter electrode for this technology uses platinum. And as you hear the name platinum, you already know that it's not very cheap. So we are just trying to take this out. So this is what we are trying to mimic or to change from platinum to another material. The other material is copper sulfide, and it has many important functions, but the most important one is the one that is basically giving or charge transferring from this liquid. So as you remember, the dye absorbs, it charge transfers, and then there is a charge transfer to the liquid, and the liquid must be decharged in this counter electrode. So that's the most important function, okay? So it must be quite efficient in doing this. So to know if we are on the right direction or not, we use basically electrochemistry. I won't go into details. And this is the material we are trying to prove that is better than platinum for this kind of application, okay? So basically the idea is to produce something industrial ready. So what we are basically producing is some kind of powder that we put it in a liquid, make a thin film, so now we don't have this problem of sizes, so we can make the film as big as we want. And this precursor, which has some organic part, goes into an oven, and then you destroy the organic part, and you come up with the inorganic thin film. That's the basic idea. I won't go into detail, but if you are interested, I can go into details. So the thing that's why I brought it here is that in doing this, you have now to think about the environment and the green chemistry. And one big problem is that depending on the organic you are using, one issue is what is soluble in. Because you see, I need to produce this powder, and this powder must be produced through a chemical process. So what we are trying to find are chemicals that are basically environmental friendly. So this is the one that we use, this geoglycolic acid is what we propose to do that. So basically we are doing this complex with geoglycolic acid, and the idea is that we make this, this material, and as I mentioned, we have to use temperature to destroy the organic part. So we must know which temperature we must go to destroy it. And with this material, we also could go to relatively smaller temperatures, 300 degrees, to get it off. So we've got these two advantages. It's soluble in water, and it's destroyed at relatively low temperatures, okay? So the material, because we are making this material at 300 degrees, it's not really a very good crystal, as you can see from the X-ray. But it's making relatively good crystalline material, but that doesn't matter so much. What is important is how it's effective in doing the job of substituting platinum, okay? So this is a small graph of a main idea. So we produce this water-based precursor, we produce this, and what I'm going to discuss with you, which is more detail of the technology, is that up to now the best materials or the best solar cells, they are basically using this electrolyte, iodine iodide, which is okay for high efficiencies, but it's not a very nice material because it's very aggressive, it's very reactive. So we try to look at for other electrolytes, and one which is especially interesting are the ones for quantum dot solar cells, which use sulfides and where platinum is really forbidden to be used, because the sulfide destroys the catalytic property of platinum. So, okay, we tried with these three types of electrolytes, and basically what I'm trying to show you is, don't care too much about all the results, but just to show that these materials are quite reproducible and stable. And if I compare the platinum with our copper sulfide, cobalt sulfide, we get this charge transfer resistance. This is the resistance to transfer charges from the electrolyte, better than platinum, but it also works with these other three types of electrolytes. So this material is also very stable, as pointed out. One of the issues that concerns solar cells, especially to compete with silicon, is that all these alternatives must be as stable as silicon, which is a very stable material. And of course, we have tested this not for years, but for days, and we get quite nice results with efficiencies which are reasonable for this type of research-oriented solar cells in the order of 8%, 7%, not the 13, which are the records. Okay. So I think you'll have to control me how much time, because I don't want to go to it. But it's easy, water-based, high efficiency, compatible with iodine-free electrolytes, which are the main results. So now changing completely technology, these perovskites materials appeared very recently, and they were the first materials that really changed the efficiency from basically 13% just in the beginning, which is quite amazing. You can see all the other technology coming from very low efficiencies to 13. This one already started in 14. And nowadays, they are in the order of 22%. So this is an amazing material and has basically brought out a lot of people to this community. There is a real rush. That's one of the problems with the polymers, the organics, because suddenly this technology appeared and everybody knows, let's forget it, let's go to perovskite. This is also something that must be said. And our contribution to this is basically, again, in a very specific point, because as you know, all devices are quite complex. So we're making a very specific contribution. But for you that maybe never seen this crystal, it's basically organic inorganic material. It has the PBI, and it has an organic molecules inside. And the amazing thing is how easy we can make it. So there are many structures, but basically the first structure that was used was mainly the same as the dye solar cell. It came from the dye solar cell community, where they were trying to get rid of the electrolyte, of the liquid. So they made it solid with the perovskite. And you can make it also very easily, very cheaply. So it's very easy to make. Okay? So the basic idea that we try to contribute was to make some kind of band engineering, in the sense that we are substituting, here you see you have TiO2 mesoporous in a kind of nanoparticles, and you have a compact layer here just before going to this contact. Now the opposite contact, the contact that I was discussing before was the contact for the holes, and this is for the electrons. And the idea is that if we could change this TiO2 compact layer for NBO05. And why is that? Because I think all Brazilians know that basically 90% or even more of the niobium on Earth is on Brazil. And niobium oxide is very close to titanium oxide. So, but it's more stable chemically. And the interesting thing from the electronic point of view is that if you look at the band structure, it has an energy level for the conduction band where the electrons are being injected a little bit below the TiO2. And what is the point? Is that by doing this, we avoid this electron going back to the perovskite, as I will show you. And this has many interesting aspects from the stability point of view. So we made solar cells out of the two structures with only TiO2 and TiO2 NB2O5. And as you can see here, there is quite a difference in their response. The TiO2, and this is the problem with the stability of perovskites, they are quite unstable. They change, for example, I'm going from the positive voltage to the negative and from negative to the positive. It's kind of a hysteresis. And with NBO2, you don't have it anymore. It disappears. And it's more stable. I won't go again into details, but the basic idea is maybe shown clearly in this cartoon. So what I'm trying to say is that one problem of the perovskites is that they're quite reactive, especially the organic part. So by making the electrons to go from here and then to here, they avoid staying in this interface and reacting with the organic part. So that's why it's not trapping charges and it's avoiding reactions. So we're doing kind of band engineering. Okay. So okay, sorry, I still have time. Otherwise, I'll go very quickly. That's the other. Now I'm going to the topic that was in the morning of Carl Leo with organic solar cells. And there again, there are many challenges from the point of view of material science. And what we are trying to avoid is one problem with one of the main parts of the solar cells you saw. It's basically a mixture of two materials, typically P3HT and PCBM or C60. And one problem of C6 or PCBM is that they tend to form this kind of clusters. And when they form these clusters, the efficiency goes down of the solar cell as a whole. Again, a problem of stability. So the challenge was basically to try to make a C60-based material, but without these problems. And to do that, one solution is to polymerize the C60. So there are many ways to do polymerization with C60, but the most stable one, which would be the best ones where the C6 would be more rigid, is this kind of structure. But this is very hard to make. To make two connections with C60 is not easy. So typically people do this kind of stuff, where the C6 are still tumbling quite a lot around. So we developed this kind of synthesis. Not me, I'm a physicist, a guy in France did that. And basically we could show that we can make this kind of polymerization. And another interesting point about this kind of azo kind of synthesis is that we don't use metals. Okay, so normally you have to move metals for the catalysis of this kind of reaction. In this case, it doesn't have. So okay, so sorry if I'm running out of going over the scene. The important thing that I would like to mention is that none of this was done alone. So the first part we did with colleagues in Italy. The second part, so the first with the dyes. The second part with the perovskites we did with colleagues in Switzerland, basically Frank Nuesch. And the third part with the University of Po, Roger Hiarns. And we did also some calculations with, for DFT that I didn't show, with people in my university. And this is not so new. This is the group that, that works directly with me. I am part of a big group. It's called the One CEPID group, which has, if I'm not wrong, about maybe 200 or 300. I don't even have the numbers. It's a very big group on material science, but I'm talking about the things that I do in my lab. And these are the people, just to show. Silvia is the one that did the perovskites. So Mirko is an Italian guy from Rome that did PhD, now he's doing a postdoc with me, did the dyes. And Bruna was the one that did the work with the fullerenes. So thank you very much.
Thank you, Carlos. So I'd like now to invite all the speakers here because we just received a message and Carlos Sampaio had to leave because he had some problems, and but I think we can now conclude this very nice section, inviting the speakers here. So please, Wesley, Lausset is here, and also Osvaldo and Carlos. Sit down. So we have more space here. So first, I would open for questions, comments, suggestions, considering all I think that we saw or what was presented.
I have a question for Carlos. I wonder if any of these technologies that we're developing is somehow going to the market, or if there is any kind of intention to do that.
Of course, that as I told you, we have always this goal in our lab to look for technologies that would be industrializable. But I'm not sure if Carlio has mentioned, but in the case of photovoltaics, the market is very aggressively taken by the silicon technology, and especially China is basically making all the cells, and there are at least quite clear indications that it's really dumping the prices of the solar cells. So at the moment, it's very hard to compete with silicon solar cells unless you go to some very specific parts of the market. So for example, in the case of the dye solar cells, it would be as with the organic solar cells, the last talk, for something like with architecture, so for facades. And also another interesting aspect with the dye solar cells is that they are in principle more efficient with low illumination. So for indoor use. So for example, we were just talking here that everybody uses smartphones, and why not use solar cells in the smartphones so that we could, they would be more useful indoors. So there is some market if you go into this direction. But actually, from the point of view of companies, we were working with basically two companies in Italy. So it was the Dysol, and there was one which is private, public, Chose, from a region close to Rome. And unfortunately, there was no real space in scaling really up. They were already in quite a intermediate size, but in Europe nowadays, it's very hard to get an industry competing with the solar cells in China. The prices are going down. And it's a new technology, and the silicon technology, as Carlo Leo mentioned, they give like 20 years. You put it in your house, and it will work for 20 years. So, and all these new technologies, we can even say that it will stay 20 years, but there is no proof. The silicon technology, there are solar cells that are working for more than, so it's already shown that it works. For the others, they are all new, as you saw. These developments are in the latest years. So it's an interesting question. It's an interesting question, but for the moment, I would say that this niche did not really appear unless you talk about the perovskites. The perovskites, there is already quite a clear sign that maybe the first generation of commercial products will be actually improving the silicon technology. So the thing that I didn't discuss with details, but silicon has a gap which is around 1.1 electron volts, which means that it's more on the infrared. So from the point of view, and while the perovskites is 1.5, so you can make what is called a tandem cell. So you can make silicon and above the perovskites, and then you have already a technology that is doing, let's say, 13%, and then you go to 18, 20%, just by doing some kind of thin film covering this already robust and very well tested technology. So there is a chance perovskite, especially in this application, I think it would be the way going for perovskite. But there are still issues. I just mentioned one of stability and stuff like that. And the other thing is that, as I told you, it has lead. It's PBI, which many people don't like it, even though it's a nano layer. It's really the quantity of grams. If you extract it in a big cell and you extract all the lead that is there, it's ridiculously small. But anyway, you talk about this for the environmentalists. Oh, you are using lead. I don't want to put lead here in my house, and it's there are many questions. But I hope I have more or less giving you this answer.
So I think there is another question there.
I wasn't sure whether the discussion was continuing there, but I'm also from the bio-religion in a way, and I hear the solar religion, and I see this problem that these two religions keep on telling one another, you know, they have the lowest footprint or the lowest investment and so on. But what occurs to me more and more, certainly because I'm now in an institute that also produces PV and storage stuff, that the complementarity is actually much larger. You know, the excess electrical capacity, the storage of that. You know, chemicals are a very good way to store it. Ammonia from one end, maybe solar fuels from another end, and particularly the ammonia contribution. If you look into more biomass, you know, this would be a great way of connecting these two worlds. Still, I you know, this sort of ideas are around already for some time, and still I kept on noting, and that is not like an issue or complaint, but I kept noting that you said, well, lower square meters for the power and so on. So how do we get these two worlds together to make sure that we really capture the benefit of both? Question can be asked to any of the
anyone,
four.
Yeah. I'll try from my point of view. He has a very clear point, that which is everybody, at least from the photovoltaics, tries to avoid, is that you have sun during the day, and most of the lighting you need at the night. So we have an issue there with energy storage. It's clear, and of course that it would be ideal if we can combine these two words in any sense, either just, as you mentioned, as a kind of energy storage, just to say, oh, I'll produce electricity and I will store this chemically by any kind of reaction. That's clearly one point. But here in Brazil, for example, these issues are even more, or a little bit more complex, in the sense that we have a lot of hydroelectricity. So photovoltaics, we will have to talk with a lot of other technologies. I agree with you, biofuels, which are very important here, should be great concern. And these are again, as our colleague pointed out, it's a multidisciplinary problem. It's not just a question of doing the best cell. We have to think about the engineering. How are we going to have these smart grids to support all this? For example, during the day, I'm producing electricity, I'm putting it into the system, and then with that, I am avoiding, for example, putting so much biomass production during the day. So it will have to have quite an interesting development in legislation and the way we use our grid. What seems to be one point of interest for the solar energy is when you think of getting out of the grid. So especially in Brazil, we have very remote places. So it would be very nice to find these solutions for places that are out of the grid, where we could combine this storage and production and have kind of a self-sufficiency inside a small town or something like that. And here in Brazil, we know 50% of our energy is lost in the transmission. So we could avoid a lot of loss in transmission if you could think about system, as you are mentioning, to produce some kind of biofuel with photovoltaics and making everything working together. So it's a very interesting and especially here in Brazil, it's a very important question.
Yeah, my target was not so much the biofuel side of it, which is an option also, but you know, the fertilizer side of the agro industry. If bio is going to be bigger, if it is, you've seen Klaus' numbers, then also fertilizer need goes up, meaning ammonia goes up. Ammonia is now already, I think, 5 or 6% of global energy use, so that must ramp up to 12 or something of that nature. So the energy requirement for that, for the Born-Haber process, is maybe this is a way of coupling these things.
So I think the question was very good too, the questions actually. And we are talking about energy now. So biomass is a way to store energy. And also transmission or transport. Could you talk a little bit about this? How you, and Grand Bio or Grand Bill here in Brazil, how you are facing this problem considering transportation? Because when we think about biorefinery, we are imagining that we are producing the biomass and the waste there, close to the pilot, to the plant, to the whatever. But how are you designing the whole system to feed your bio industry? Because actually, this is a big problem, I think. If you are thinking about 50%, with solar electricity or whatever, can you imagine about biomass, soybeans or etc. that we are producing here in Brazil, from the where we are producing to the point that we are processing this biomass? So I just mentioned soybean, but of course we have much more than this corn and of course sugarcane.
I'm going to start, and Wesley, if you want to jump in at any time. So in our particular case, we are in a very privileged location in the state of Alagoas. So the logistics is we have a very privileged location, because the places where we collect the biomass are close to the plant. We are very, very close to the port. The main destination of the cellulosic ethanol that we produce at Bioflex is the US or Europe, because these countries pay a premium over the price. So today, cellulosic ethanol worth at least twice the price of hydrous ethanol here in Brazil, because of the premium that are paid in the US and Europe. So we are in a very good location in terms of where we collect the fuel, the sugarcane straw. Wesley showed all the logistics that are involved. We have worked together with the equipment manufacturer to develop the equipment to collect the straw. So this is the additional cost to the let's say to the first plants that we had to support, and that we have this knowledge for the second, the third plant now, but we spent a lot of money with the development of all this equipment. But your question is very interesting because of all these losses that we have in the transmission. Brazil is a continental country, so we have answering the question made by our colleague. So we have to combine all the sources of electricity in a country as Brazil, because certain areas will be attended by solar or windy electricity, and other places are so far that you cannot take the electricity to there. So you use better liquid fuel, so as a biofuel. And this your question about the problems that we have with infrastructure in Brazil. So just to give an example, that we are now producing corn ethanol in the state of Mato Grosso and Mato Grosso do Sul, and not because we are more competitive to produce corn ethanol in these regions, but because logistics is so problematic to bring the ethanol from the middle of the state of Alagoas or Goiás or Mato Grosso to the south region, that instead of transporting the corn, these plants are now, the farmers are now selling the corn to produce corn ethanol in Brazil. So we are now competitive because the corn in these regions are so cheap that it's better for you to produce ethanol instead of selling and transporting all this corn to the south or to the port. So because of the problem that we have in the infrastructure in these places, we created a new business in this region. No, not because our ability to develop a new industry, but because as an answer to the infrastructure problem that we have in the region.
Just to make some comments, I think oil and coal have evolved during maybe a bit more than 1 century to become almost the single solution of energy supply to the world. I don't believe we will find one single solution to replace oil or coal. So alternative energy, let's say wind, solar, biofuels, will have to be combined in order to supply a competitive solution for oil and coal. So I agree with you when you say why I produce corn to send to US to make ethanol in US, and I import ethanol from São Paulo to feed the cars in Mato Grosso. So it doesn't make sense, but it is competitive because of this logistic aspect. So it makes sense. So we don't. I wouldn't see this as a corn ethanol as a competition for sugarcane ethanol. It's just a local solution. I would say the same for solar cells in some areas. I believe, especially the electricity sector will change dramatically in a few years, because we'll move from a centralized production model and distribution to a distributed production model, which will become possible with new technologies like solar cells, with wind, with small hydroelectrics where it's applicable. So I believe that the solution for these two main supplies of energy will come from different applications of these kind of technologies.
Yes. So in answer to your question, we looked at feedstock supply chain, how the whole from the beginning, from land use, feedstocks, the transportation, the integration with the different technologies for processing, depending on what the end product would be. And there's two main themes that rose, which is one is integrated resource assessment. So just this week, I saw a startup company trying to find funds to produce the necessary data to make intelligent conclusions on how to establish this chain, the supply chain. And the other thing is this idea of multifunctional landscapes, where you're going to have different things coming out of the land. You have food, you have energy, you have ecosystems. You have to try to see how best to use the land and how to integrate so that it comes with the most of the benefits. So for the multifunctional landscapes, there's not a lot of real-world solutions, examples. We see some kind of boutique examples, of people that are trying to see how they can make the most out of their land, of their industry. But what I think is emerging is a new market for residues. So let's see how this will all tie up. But there's a lot of young people trying to put together solutions for these new problems that we are going to have. And I agree, the oil companies had 100 years. We're just starting. But in Brazil, we have a biomass market already. So I think we are in a good position to make good advances. Any comments?
I'm not sure if I have a question as complex as the other ones, but as a recent graduate chemical engineer, I would like to ask Grand Bio because if I remember correctly, the company bridges the academical and the industrial sector, and when you scale up, my curiosity is, when you scale up this project or this reactor, do you face a lot of challenges because sometimes when you scale up, you can't maintain the pressure or the same temperature as you're in the lab scale. So my question is, in the real life, do you face a lot of challenges when you scale up? The industry from lab scale to yeah.
That's for you, from engineer to engineer.
Thank you. This is exactly the point I wanted to make. So what is stopping us to get to our nominal capacity? It's not the enzymes, it's not the yeast. It is the heat exchanger, it's the pump, it's the electric driver, it's the screwdriver that transports the... So this is, when we talk about technology risk, everybody think about the biotechnology risk in this industry, and I believe this is behind. And what is really our challenge today is the engineering challenge of making these chemical reactions, let's say, or biochemical process that happens at small scale and at big scale work continuously. So it works in big scale as well. The issue is it plugs, it leaks, it corrodes. We have erosion, abrasion, we have several material problems that we don't see in the lab because we're not looking at this kind of problem, because you don't know they exist until you go up to the industrial scale. So we are still facing this kind of problem, but this is not our privilege. I mean, every new technology will face trouble in scaling up. So it's not, let's say, I cannot say this is a surprise. It's not in general considered in the business plans we make. But this kind of trouble will always happen in new technologies. That's why I like the approach of saying, okay, for new things, if you try to apply the same type of risk analysis you do for the conventional technology, we will have better prices, for sure.
Can I make one question to my colleagues here? No, of course. No, one thing that it's like maybe a very naive but question is that normally when I see this agribusiness, we're always looking for the optimizing the best plant and then multiplying it and making it as many as you can. And this is, of course, in principle okay, but also nature finds a way to destroy it. And if there is some kind of plague or something like that, it attacks one and attacks everybody. So is this some kind of concern of making something more natural, like we have the biodiversity, you don't have a forest of all trees is the same gene. If there is this kind of approach, because I think in the future maybe one solution may work for some years, but afterwards, as we are seeing with I take this from the orange,
Yeah, so one of the problems for the biotech industry of sugarcane or the breeding, even the traditional breeders, is that you never, any grower, it does not grow only one kind of genome. It never does, even if it looks homogeneous. They are all different varieties, and they try to keep up and change and always develop new ones, because if there is a plague, you don't want it to go, your whole plantation to go away. The problem with that is that you sequence one genome, it's not enough. You have to sequence all the genomes if you want to use genomics to aid the breeding. So it is a solution for them and a problem for us that deal with the genomes. In terms of using biodiversity, then you have a problem of the scale, because if everything you want to produce, we're not talking about a small thing that will be solving a niche problem. We're talking about big world global problems that you need a lot of, because we have to substitute, in the case of energy, you need to substitute for the oil reserves that are plentiful, the coal that is plentiful. So I don't think biodiversity will be now the answer, but you may find plants that you need to breed until they become something that are able to produce in quantities. And the answer is, if these multifunctional landscapes become a reality, if we have more studies, perhaps you will not even see one kind of homogeneous plantation anymore. But so far, we still have, I'm not convinced it is such a big problem that we have monocultures. I don't think so.
So, any other question or comment? Would you like to raise another question? Are you happy? Okay. So, first I would like to say thank you very much, really, because we are concluding our academic semester, and I know for my colleagues from this point of view, and also I know when we are working in companies, we are very busy, and we are in the middle of the IUPAC meeting too. So it's very nice that we could combine all these very nice people from different countries, continents actually, and point of views. So it's so important to do this because we have a lot of very good questions, and we need a lot of very good answers too that are not easy to find, to combine. When we think about biorefinery, it seems a miracle that we will resolve a lot of things, but actually we need a flexible model. I don't know, the fourth generation, or maybe, I don't know, how we can put everything together to face this challenging, not only moment, because we'll be not worse, but more complex, I think. But we need to do what we are doing here, to stop, to think together, to try to connect to people who are also doing researches, business, and starting new companies. So it's really important. This is not waste of time, because we always think about time. Time is not renewable, and we need to make the best that we can with our time, with very good people. So it was an honor, I think, to be here, for all of us. And I'd like to say thank you very much for also the Professor Krieger, our pro-rector of research, and also the IEA, the Institute for Advanced Studies, and the IUPAC again, and also the German Office for Research and Technology. So we have a lot of German institutions there. It's like an umbrella, German umbrella. And of course, for all of you that are here until now, and I think we need to conclude now. So thanks again for your time, and we will meet, I think, in another occasion again. Thanks, really.